So, welcome everybody to today's presentation organized by the Southeast branch. My name is Gosia Szypulska and I am the current chair for the Southeast branch. And I would like to introduce you today's presenter, Colin Murphy. He's an engineering manager for Tideway West. And he will be presenting to us on a very, very interesting project. The title of today's presentation is Building the Biggest Thames Water Tideway. Before we start, I would like to ask everyone to mute their microphones and turn off the cameras. This helps with the quality of the call. There is also the chat facility available where you can post your comments or ask questions. We will be answering questions when Colin finishes the presentation. And if we cannot answer all the questions online, we will answer them offline. So last thing, the presentation is being recorded and it will be available on the Pipeline Industries Guild YouTube channel. So I think we're ready. I'll pass it on to Colin.
Gosia, thanks very much. Good morning or good afternoon even to everybody. Gosia, if you could just let me know, can you see the presentation on the screen? Yeah.
Yes, yes.
Okay, lovely stuff. Okay, I'll get straight into it. I'll turn off my video just to save bandwidth as well. Just bear with me now. Okay. Okay, well, thank you for inviting me to present to you all this afternoon. My name is Colin Murphy, as Gosia says. I'm engineering manager for Tideway on the western section of the Tideway project. I'm a civil engineer by trade. My skill set is around major hydraulic structures, major hydraulic infrastructure. I've been working on Tideway now for approximately 10 and a half, if not 11 years, having worked on the design team originally and taken the scheme through tender and into procurement and now into delivery. We've been in the delivery phase now for approximately nearly 6 years. We've probably got another 2 to 3 to run. Tideway is a huge topic. So the presentation today is designed to give you a sort of an overview of where we've come from, where we're at now and where we're going. I think you could probably stretch out a whole pile of other presentations just on individual elements on Tideway alone. So I'll do my best to give you a good flavour for what's happening. So I'll just move on through this now. So what is Tideway? Project need and the scope, what are we all about? So Thames Tideway is the biggest infrastructure project ever undertaken by the UK water industry. Based in London, it's about 25 kilometres of sewage interception, storage and transfer tunnels. In terms of depth, it runs roughly from about 35 metres to about 65 metres below London, predominantly running beneath the River Thames. Sorry, if everyone could mute their microphones there, getting some feedback. Thank you. Tideway is comprised of one major main tunnel, which in diameter runs from about 6.5 metres internal to about 7.2, which is about the width of an average UK single carriageway road, about 2.5 London buses in width. And we have 2 connection tunnels which connect into it, which are 2.6 to 3.2 metres in diameter. And Tideway is comprised of about 24 construction sites, 11 of which are riverside, and some of those riverside ones are either adjacent to the river or actually within the River Thames itself. And Tideway plus the Lee Tunnel, once fully completed, will provide about 1.6 million cubic metres of storage capacity for sewage in London. And you know, the water industry loves it, the equivalent to Olympic swimming pools. I've given it there, it's about 600 Olympic swimming pools. That seems to be the standard measurement for a hydraulic project these days. So in terms of route, this is the overview. We're running from Acton in the west, which is number 1 up there in Ealing on the left of the page. We run down through Hammersmith, which is number 2, down into Barnes, Putney, and then we get to Wandsworth, Fulham. Number 7 is Carnworth Road, which is a main drive site for one of our TBMs. And that's where we receive the Frogmore connection tunnel. So that's a smaller tunnel, about 3 metres internal diameter. And we proceed on down into central London. So Kirtling Street is another drive site. That's at Battersea. and then on up through following the Thames into central London. Beyond Tower Bridge, we get to number 17, which is Chambers Wharf. That's where we receive the Greenwich connection tunnel. And then the tunnel proceeds on underneath Tower Hamlets, underneath the Limehouse Cut up to Abbey Mills. And that's where we connect into the Lee Tunnel, which is already in operation and functioning today as a sewage transfer facility to Beckton Sewage Treatment Works. In terms of scale, context, just to give you an idea what we're dealing with here, so that the Tideway peak flow extreme storm capacity is circa 140 cubic meters per second. I'm sure the Pipeline Guild is well familiar with cubic meters per second. For those of you not, the sort of average flow in the River Thames today on a median tide is about 60 to 70 cubic meters per second, with peak in the river about 275. So we could broadly take a fair chunk of the Thames into the tunnel in a hypothetical scenario, obviously, but suffice to say some major hydraulic capacity there. In terms of design ranges and what we're trying to take, and I'll get more into what we're trying to take in just a bit, but the design event that we're dealing with here is a 1 in 15 year probability storm. And what that means is we're dealing with the overflow from the London sewage network in a 1 in 15 year probability storm. The site design flows that we deal with, so I've mentioned we've got 24 sites. At each of these sites, we've got a combined sewer overflow, which I'll explain more about in a second. But each of these overflows delivers anywhere from 1 cubic meter per second up to about 55 cubic meters per second. So in context, a traditional builder skip outside a domestic dwelling might have about 3 cubic meters of storage. So at one of our example sites, Hammersmith, we deal with 43 cubic meters per second, which would equate to about 14 mini skips of sewage a second that we need to turn and intercept and convey to a tunnel. To understand the routing and where we've come from, it's quite pertinent to understand the sort of history of the London sewage network. So this is just an overview of the old rivers of London, which ultimately, by the time we got to sort of 1850 era, a lot of these had been culverted over to form the main sewers of London. And by 1856, I think we sort of had a version of what you can see on the screen here, where effectively all foul sewage was being placed into these what were rivers, then became sewers, and just going straight into the river with no treatment whatsoever. 1858, as you'd be aware, London had the Great Stink, the cholera epidemic. A lot of people lost their lives. It was a serious event, and a chap called Joseph Bazalgette was drafted in to resolve the issue. And over the following 20 years or so, Bazalgette instigated an extensive scheme of sewer upgrade and sewage infrastructure upgrade, comprising anywhere between sort of 130 odd kilometres of main sewers and 1,100 miles of street sewers, coupled with some major pumping stations at Deptford and Crossness and Abbey Mills. But for all intents and purposes, what he strove to do was to intercept the sewage that was in each of those old rivers. And rather than them discharging straight into the river, he picked up that sewage and conveyed it east to either Beckton on the north side of the Thames or Crossness on the south side of the Thames. Into that system, he designed a series of overflows, which were envisaged as emergency relief valves, which is really where we come along. And I'll explain a bit more about them in a second. This is a typical example of what he built. This is the Embankment in London. Many of you will be very familiar with it. So on the section on the bottom of the screen, you can see the current sort of tube line position. On the left, you've got the low level relief sewer. So that would be conveying flow to Beckton ultimately today. And you've got a utility subway above it. And a picture on the top left is a fairly recent picture. It's within the last couple of years. Of part of one of the low-level sewers in that general vicinity. And today, what Bazalgette built back then forms the spine of the modern London sewage system. And it's in very, very good condition. What Bazalgette built, I've seen it myself, the sort of brickwork and the quality of what was done in the 1850s and 60s is exemplary. There's absolutely nothing wrong with it. It's extremely efficient at delivering foul flows to the sewage treatment works out east. It's extremely efficient at delivering normal rainfall runoff. So that the key point here is that the system in London is combined. It receives surface water and foul flows. So it's extremely efficient at delivering normal runoff to the surface, to the sewage treatment works, and extremely efficient at delivering overflow to the river at the combined sewer overflows. So I mentioned them just now. So Bazalgette built these structures, close to 40 of these along the Thames, into those low-level relief sewers. And the purpose of them was to effectively avoid flooding of London with sewage. So when you get a storm event which exceeded the capacity of those low-level reliefs, these CSOs would kick in, and rather than flooding the streets, the sewage would be discharged into the river. When Bazalgette designed his system in 1860, he envisaged a design capacity around 4 million people. So he had about 2 million people at the time in London. He factored in a doubling of that to 4 million. And he considered that those overflows into the river would operate about 4 times a year. 4 million people was achieved in 1920 in London. By 2019, we had 8.8 million. And of course, by sort of 2160, it's projected that we'll have around 16 million in London. So what does that do to the overflow system? So in 2014, there was 62 million cubic meters of raw sewage discharged into the tidal River Thames, which equates to about 50 discharges on average in a typical year from each of these CSOs, which is a far cry from the 4 discharges he'd envisaged back in the day. In a typical year, so the difference there between 2014 and a typical year is that 2014 was exceptionally wet. That's a year of great flooding in the UK. In a more normal typical year, we experienced about 39 million cubic meters of sewage discharging to the Thames, about 50 to 60 CSO discharges. Obviously, from an environmental standpoint, that's not great. The nature of the tidal Thames means that sewage pollution stays within the Thames in the immediate vicinity of the discharge for weeks. Prior to constructing Tideway, a number of tests were done on the river to understand how long it actually takes sewage to get away from Hammersmith out to the tidal, to the tidal estuary. It could take up to 2 weeks for sewage to leave Hammersmith and ultimately get out to the sea. Just to give you a sort of a context for how long it takes. That obviously affects dissolved oxygen in the river, ecological health, and habitat in the river. Not to mention the sort of human impact. The river is an amenity feature, of course, especially in the upper reaches. It's a health threat to river users, walkers, rowers, anglers using the foreshore. And of course, from a legal perspective, it meant that the UK is failing to comply with the EU Urban Wastewater Treatment Directive. So the tidal Thames didn't achieve a good status as reflected in the Wastewater Framework Directive requirements. So there's an overview of where all those CSOs are, but suffice it to say there's the vast majority of the big offending ones are sort of in central London. Abbey Mills out in East is another large one, but they're right through the tidal extent from Teddington down to Beckton. So before we could reach a solution, it was key to sort of understand how these CSOs operate. How does the London catchment drive those CSOs? When do they open? What are they discharging? So there was a number of years worth, nearly 20 years worth of data collection and assessment done by Thames Water and the project team to understand sort of rainfall, what surfaces were connected, what the collection system was that was delivering flows into the system, how are they controlled. So not all of these CSOs are gravity operated. Some of them are pumped CSOs, particularly Hammersmith. That's an example of a pumped CSO where the rainfall in an extreme event arrives at that pumping station and it's lifted up into the river. That exercise, coupled with simulation of storm events across the wider London area, allowed the team really to get a handle on what sort of flows would we be expecting to have into Tideway. What was the right design storm? What was the right design duration to be designing any potential scheme to cater for? That also looked at sort of future seasonal changes, rainfall intensity increase, and population and temperature change over the next 120 years. So in terms of developing the solution, back in 2001, the Thames Tideway Strategic Study was set up to consider the impact of these CSOs and what could be done about it. In 2004, there was infraction proceedings against the UK, and so on until 2011. The Tideway project was costed at about 4.1. And in 2012, the European Court of Justice ruled that the UK had breached the Urban Wastewater Treatment Directive, and the UK needed to comply as soon as possible. So in that strategic study in 01, it primarily looked at these four types of solutions. Was a solution upstream of the network viable, i.e. a sort of a SUDS solution, dealing with the rainfall runoff? Was there something that could be done in the system? Was it inline tanks, for example? Did it need to be dealt with at the CSOs, or indeed, number four, could it be dealt with in the river? Just accepting the fact that the sewage went into the river and deal with it there. Number three was selected, a scheme that would deal with it at the CSOs. So rather than the emergency overflow discharging to the river, we pick it up at the CSOs and drop it into a storage tunnel and transfer it to treatment. And that really was the preferred option, I think, because of scale, volume. I don't think anyone has ever really said, certainly number one and number two, that they weren't viable from an engineering perspective, but from a pure volumetric scale issue. When you start thinking about the sort of flows we're trying to deal with, SUDS, the land take just wasn't really there, the land availability. So number three was selected, and that was worked into an overarching tideway improvement scheme, which was made up of three bits: the sewage works upgrades done in the sort of 2000s and into 2010s, Lee Tunnel, which was constructed between Abbey Mills and Beckton in the sort of early 2010s, and Thames Tideway Tunnel, which is what we're here now talking about. And that's an overview of how they lie. You can see the pumping station upgrades. You can see Abbey Mills running to Beckton, and then the Tideway Tunnel running from Acton to Abbey Mills. So developing the scheme, the fundamentals, obviously we wanted to maximise the use of the sewer system, maximise the use of capacity at Beckton and Crossness. There was a need to control the CSO discharges to get it from the 50 average per year down to the original Bazalgette design frequency of 4. No increase in flooding risk, obviously, to the system. We wanted a scheme that would control water levels to limit the need for extensive above ground structures. Obviously, being within London, land is a premium. We wanted to control inflow to reduce risks associated with potential adverse pneumatic and transient conditions, which obviously is a major issue, as you'll all be aware, dealing with pipelines, transients and backhammer and pneumatic issues. Air in tunnels is a serious issue. So something we've striven to avoid and deal with. And we wanted it to have simple operating rules, so avoid a complex, opening closing scenario, avoid dependencies on any live forecasting, make it as much of a dumb system as you could physically do in this day and age, make it very, very user friendly and simple to use. The scheme was planned and executed through the DCO, the Development Consent Order, so that was about 6 years of project development, planning and extensive consultation. We had about 114 odd days of public exhibitions with 200 odd public meetings. And that saw us take 373 potential sites down to today's scheme selection of 24. You can see a photograph of that DCO application. That believe it or not is one application in that whole series of boxes that was made, and ultimately planning was granted for the scheme as we're delivering it today. So what are we trying to do? So in terms of hydraulics, very simply, this is what we're all about. There's an existing combined sewer overflow discharging to the river. We're constructing some form of a concrete chamber on that CSO line. We're dropping and turning flows through a connection culvert, taking it down into a drop shaft. These shafts range in diameter from 6 to 25 meters in diameter, and range in depth from 35 to close to 70 meters in depth. And then the flow is taken through a connection tunnel and then into the main tunnel and on down the river. This is a schematic through a 3D schematic through Blackfriars, which would be one of our major sites in central London. So this just harks back to that Bazalgette section I showed you earlier on with the tube line on the right hand side. You've got just to the left of the tube line the existing low level relief sewer with the utilities corridor above it, and then our new foreshore structure built out into the river to house our hydraulic infrastructure, taking flows through a series of penstocks and flap valves into what we call a vortex drop tube, vortex generator and drop tube, down into the shaft, into a stilling basin, and then through some baffle walls into the connection tunnel and into the main tunnel. So obviously major design challenges in trying to deliver something like this through London. We're fairly constrained as to where we can be. The CSO interception sites need to be immediately adjacent to outfalls. We obviously need to be close to or at the river. We need 3 main drive sites for tunneling, and a drive site in tunneling is about the equivalent of roughly about 2 football pitches of land is what we required. On sites where we weren't driving TBMs but are just purely intercepting flows, you'd need about 1 to 2 tennis courts worth of land. And as I've said, our shaft sizes range from 6 to 25 meters in diameter, and we're trying to deliver this in a very congested urban environment. Using brownfield land instead of greenfield where possible was a key driver for us, trying to use Thames water sites where applicable. We obviously need to take account of local receptors, local stakeholders. Where land is unavailable, it was clear we'd need new foreshore sites. So like that photograph I just showed you just a second ago, a new foreshore site providing permanent public space and public amenity in the river. So Blackfriars and Putney are 2 very good examples of that. And we wanted to take the opportunity to build in environmental mitigation and betterment where we could. So we've got facilities such as intertidal terraces. We've done half-tide weir works at Dormay Street in Wandsworth, and a variety of other things across London in our schemes, with the main aim really of trying to reconnect Londoners to the River Thames through new spaces and amenities. So although we're building a very, very large sewer, we wanted to give something back to London as well and make it part of the city. These are just some old examples of what a typical foreshore construction site looks like. You know, there's the sheet pile cofferdam in the river on the top left. You've got a small shaft example. I think that's about an 8 meter, maybe 10 meter diameter, segmentally lined shaft on the bottom right hand side. That would be a baby shaft on Tideway. We've got an example of a drive site here. I think this is an very old photograph from East London from back in the day, but you can see quite a substantial undertaking, a drive site. And then that photograph on the right hand side is the TBM for the Lee Tunnel. This photograph's taken quite a long time ago now, but just to give you a sense of scale of these TBMs, that was an 8.85 meter internal. And that's that particular TBM actually at the bottom of Lee Tunnel. So onwards today, this is an older photograph, 2016, but this gives you an idea of a foreshore site on Tideway. This is Chambers Wharf. This is a drive site in East, just below Tower Bridge. If you happen to walk across Tower Bridge and look downstream, you'll see this site. It's currently live in operation. In terms of thinking about where we could put these sites and how to work them into London, you know, as I said, congested urban environment, road safety concerns. So there was a massive desire and a target to move as much traffic onto the river as we physically could, and try to remove vehicles from the road. Air and noise quality was a huge concern to us. The quantities and volume of material that we're moving and when we're doing it, the construction durations, how long we're going to take to do it. An awful amount of work went into that. An appreciation that, you know, with so many sites through London, that we have sites in close proximity to each other, so there could be a cumulative effect on on third parties, on the local stakeholders. You know, typically from each site you can see another 2. Obviously personnel changes, so I'm not entirely sure, but I think on Tideway currently we're operating at about 3,000 to 3,500 staff in total. So we needed to be very clear on timing of when Tideway could actually be delivered and how could the industry react to deliver resource to the job. And of course, talking about the river, you know, existing construction marine logistics, you know, we were faced with a sort of an aging fleet and a lack of resource, or indeed a lack of trained operatives. So these are the challenges at the start of the job in terms of logistics. Environmental consideration, again, you know, major commitment to environmental compliance through the DCO. Huge topic. Intensive monitoring throughout the DCO period, intensive monitoring through construction, and a hell of a lot of mitigation built into the scheme, both pre, during and post construction. I've mentioned more by river, and we had a huge scheme of archaeological dig at the start of the job as well. These 3D graphics I've thrown up here just to give you an example of the sort of lengths we've gone to at Tideway in terms of mitigation. So this is an acoustic shed. This is built, it's been in operation now for about 4 years at Carmouth Road. And that shed is founded on over 40 deep piles. It's 83 meters long, it's 29 meters wide by 24 meters high. So a major civil engineering feat in itself, just to provide sort of acoustic protection to the works and sort of minimise the impact to our neighbours. So Tideway took this very, very seriously, our impact on the neighbours. I'll move on. Obviously, interfaces with third-party infrastructure, a huge item when we think particularly about tunnelling and settlement. As all you will be aware with pipelines, very similar story. You know, through London, we've been interfacing with 75 live bridges, about 20 kilometres of river walls, 50 in-river structures, 45 tunnels, including sort of tube lines and major utilities, sewers, 18 kilometres of those, water mains, 15 kilometres, gas mains, 34 kilometres, and you know, nearly 1,300 odd buildings that we've interfaced, as well as 24 listed buildings. So I think in total we've interfaced with about 125,000 stakeholders across London through the scheme. So a massive sort of third-party exercise to be able to deliver the scheme. Let me just skip on here. So in terms of tunnelling under London, we are faced with the challenge that we've got varying geological conditions through London. So in west, that western section, what I'm responsible for is that bit from Acton to Carnwath Road, which is predominantly through clay, which is the preferred material. It's good, robust, firm material to tunnel through. As we go beyond Carnwath through Kirtling and into Chambers Wharf, we're in the sort of Lambeth area. Sands and gravel's a little bit more difficult to tunnel in, and then east we're dealing with chalk, which has its own challenges from Chambers to Abbey Mills. Why I'm showing you this is that ultimately the ground conditions drove the way we packaged up the project in the long run. That, you know, the west contract came about because it's predominantly in clay, so that had a very specific form of TBM and a very sort of specific set of engineering, whereas central and east would be different in their own respects. The drive strategy is to drive from Carnwath Road in west to Acton storm tanks, simultaneously driving from Kirtling Street to Carnwath Road east to west, and from Kirtling Street to Chambers Wharf to the east, and from Chambers Wharf to Abbey Mills. And today, right now, the west section is complete, as well as the central section and east is currently in progress in terms of primary lining. But the differing ground conditions meant we had different forms of TBMs on the job. We've had EPB TBMs and slurry shield TBMs, slurry shield down in east in the chalk. And we've also had a lot of open face excavation and pipe jacking on the smaller connection tunnels. We've also had multiple shaft construction techniques. We've pretty much done it all on Tideway. I think all our shafts are down now on the job. But we've seen everything from secant piling to sheet piling, sprayed concrete, segmental lining, right through to D-walls, diaphragm walls in east. And you know, each of these and how these shafts have been constructed in London, I think there's some really fascinating, innovative stuff that's gone on within this that I'd love to be able to get into here, but I just don't have the time in this particular presentation today. In terms of engineering challenge, we have a 120-year design life, which is fairly onerous. We're concerned about dissipating energy and minimizing air entrainment, as I said. We want to avoid air getting into this tunnel. We need to provide mechanical ventilation and air treatment to keep the tunnel environment fresh and reduce risk of odorous air release at shafts. And you know, the old cliche of sort of open heart surgery on a live patient, we're doing something very similar, where we're constructing those interception chambers around live CSOs with some fairly considerable flows in them. So we have some fairly considerable fluming works going on and sort of live flow works in a live toll environment. So obviously we work heavily with Thames Water to be able to execute these works. But again, some fascinating stuff in some of those sites, particularly Hammersmith. And I think in the long term, we obviously need to provide suitable operational and maintenance access for 120 years in public, private amenity space. So from a hydraulic perspective, I've talked about the fact that, you know, we're dealing with some very large flows. We are trying to drop this flow anywhere from from 25 meters plus. I think our deepest drop is about 60 meters, 55 meters. So hydraulic energy management and pneumatic management are very important. In terms of pneumatics and transients, big exercise was done to understand how in a storm event how the tunnel would fill. You know, we could have heavy storms in the West London, but nothing going on in East, and throughout the day that storm front could move across the tunnel extent, and we need to be very cognizant of how the tunnel fills and what sort of storage volumes we have at different durations, and ultimately how much energy we're putting into the tunnel and where does that go. So there's a lot of CFD modeling done and a lot of physical modeling done in the States and in the UK to verify and validate you know, our geometry on the scheme. And in all of that, you know, obviously aware of surges and transients. Now, I do have a series of videos, but I don't think I'll try and play them here online because we probably break the system. But I think surges and transients are effectively where the water level in the tunnel is rising and falling dramatically, very, very quickly. On tideway in certain extreme events, we have the capability to drop the water level by anywhere up to 10 meters per second, which is considerable rise and fall of level within these shafts. So if you can think of air within those shafts and water levels rising and falling, if you don't manage the air pressures and water rise and fall, you will have considerable problems with pressure release and damage to a structure. So we've spent a lot of time and a lot of design work on trying to get this right. And that's pretty much everything I've just explained. So what does this look like in real life? This is a 3D model of a scheme which is pretty much built now at Dormay Street. We're in the final throes of this now. So on the left hand side, we've got the incoming CSO. Flows drop into an interception chamber and then away to the right through a connection culvert through a chamber which houses a penstock. So our penstocks on the job are of the order of sort of 2.2 to 3 meters square. We've got flap valves, you know, on this side it's a single flap valve. I think it's a 1.5 by 1 meter deep. On other sites we might have up to 8 flap valves of sort of 2 meter square proportions. So fairly reasonably large penstocks and flap valves and a lot of them. So flows are conveyed through the valve chamber and then into the vortex generator, down the vortex drop tube and into the shaft. I'll explain a little bit about this vortex drop tube. What it's trying to do here is we take the flows, we drop it down a ramp, we increase the velocity of the flow. At the same time, we decrease the width of the channel that it's within. We squeeze it, increase the velocity, and then we spit it against the inside of a tube. We induce a centrifugal force on that flow, so we pin it to the outside wall of that tube and allow the flow to spin. So what we're trying to do is squeeze the air, any air that's entrained in that flow, we try to squeeze it out in the vortex tube through the centrifugal force. And then when we drop it out at the bottom, it's obviously got a hell of a lot of energy because we've just increased it and dropped it in velocity. We have stilling basins at the bottom of the shaft to immediately cam it all down and take it down to less than 5 meters per second and take it out into the tunnel and away down to East London. The vortex drop tubes themselves are considerable structures, which I'll show you some pictures of in a second. This is just a slide to indicate that we've sort of 3 basic control points on how we control levels in Tideway. You know, effectively it's just level control. We reach a certain level where we start closing the CSO penstock, so we stop flow coming into the tunnel. We can bring on pumping stations, so we do have a pumping station at the eastern end of the job, obviously where the flow is lifted up into the Beckton treatment works. And then we ultimately close down Abbey Mills pumping station. And at this stage, you're in an extreme weather event, and you're sort of at the period where design capacity has been breached and the tunnel is filled to the brim, which is a very, very rare event. This is CFD modeling of a typical event on one of our sites. It's quite an old sketch, but I just threw it in here to give you a flavour for what the flows are doing. Blue being a sort of a calmer water velocity, reds and greens being a bit faster. But you can see the flows spinning through the vortex drop tube and dropping out to the base of the shaft. This here is some of our air modelling that was done. So that's really to to understand what air is left in the system at the base of the shaft and what we need to do about it. So we quickly understood that we would still have air left in the soffit of the tunnel that we'd need to take out. So on the left-hand end of this sort of this tunnel length here, we've got a restrictor wall, and that just serves to slow down the flow and allow us to egress bubbles up through a deaeration vent and away to the surface. So that the plan being that by the time flow gets through that restrictor wall, most if not all of the air has been removed from the flow. These are just some overviews of the kind of physical modeling that was done to validate the design. Not much to say about it. Again, there's some videos here, but you can maybe see them. I don't know, are they working too well? But you get the gist. This is a video. I just wanted to show you if this works. I hope it does. Maybe not. Just wanted to give you a feel for the scale of our Vortex drop tubes. I hope that came through okay. I'll just move on to the next slide. And that's a picture of our Hammersmith drop tube being lifted into place earlier this year. It's a huge exercise and very rewarding for me personally to see that, having worked on that for so many years. Pretty cool. That's a picture of our Vortex tube in Hammersmith from the base, and as we stand on Tideway, I think we've installed about 6 of these across Tideway now. We're well into it. I've mentioned air quite a few times, so this is all about another design challenge we've had, which is dealing with sort of odorous air. And we have at each of our sites, we either have active or passive ventilation, where we can take odorous air through what we call air treatment chambers, where we've got carbon media to effectively clean that air. And again, there's been extensive modeling undertaken on that sort of strategy and how it works. But in a nutshell, at all of our sites, we have some form of a ventilation column which discharges clean air. At 2 of our sites, we've got 12-meter high ventilation columns, but at most of our active sites, or most of our passive sites, they're up to about 5 meters high. And our design sort of inspiration really was to try to hide these things and not make them look like vents in London. That's an example of a vent on the left, just near Bank. And on the right hand side is our version of events, sort of a twisted column effect. And these are now being cast and will be installed on some of our sites later in the year. And that's just a shot of our air treatment chamber at Dormey Street, showing air coming from the shaft through a duct through the chamber, heading to the right up into a kiosk. And on most, if not all of our sites, we've got a kiosk which houses all our mechanical, electrical and ventilation equipment. So that's everything from dampers to the electrical kit and the sort of hydraulic power packs and all that sort of stuff for penstock driving and SCADA telemetry. And they've been quite trying to have an above ground structure on some of these sites has been very challenging. But really we didn't want operatives to have to enter confined spaces as much as possible, hence the need for these above ground kiosks. And we've gone to great lengths to try to make them as aesthetic as possible. This is one of our sites at King George's Park. You can see the kiosk, the sort of lozenge shaped building with the vent column just to the left of it. And this is an artist's impression of that. And this is what's been built right now. The shaft is in, all below ground works are in place, and that kiosk is currently being built. And we should be complete the main work at King George's this particular site in about 6 to 8 months. So where we're at today, main tunneling, just to flash through and finish up with some photographs for all of you. So all of our main tunnels and all our main drive shafts are excavated. This is a shot of one of our shafts in east is on the left hand side, and Carmouth Road is on the right hand side. Of particular note on the photographs on the right hand side, you see the hole protruding about halfway down the shaft. That's the entrance for the Frogmore connection tunnel, and we actually brought the Frogmore connection tunnel in on a deck. I've got a photograph of that in just a second. This is an overview of Kirtling Street drive site, but again, just to sort of support what we're seeing in the following photograph. You got muck barges taking muck away from the tunneling. You've got segment storage, so segments come in by river, they come into that shed, they go down into the shaft, the pit bottom, and then they're taken up to the face and installed in the tunnel. And at the same time, muck is coming back from the TBM and going back out onto muck barges, and that's been massively successful. And that's just an example of the sort of marine infrastructure being installed at Kirtling Street. This is an older picture now, it's probably about 3 years old. Yeah, that's that. This is one of our TBMs, main tunnel D. So this would be out east. So this is Selina. And following photograph here, this is one of our main tunnels. I think this is in west. This is just showing the rail system going up to the TBM. To facilitate the muck away and segments coming in. I mentioned the Frogmore connection tunnel. We brought it in halfway up this shaft because of levels, which is pretty unique in our world of tunneling to do something like this. But you've got, sort of a 3.5 meter outside diameter Frogmore connection tunnel TBM here, built on this temporary works deck, which is another 14 meters above the invert of the shaft there, where the guys are working on the main tunnel. Beneath it, so a pretty nifty bit of work there, Frogmore. There's another one of our TBMs breaking through at Chambers Wharf down in east. And currently in main tunnel, both in central and in west, we are secondary lining now. So I haven't mentioned that our tunnels have a primary and a secondary lining. The reason for that is they work in composite to achieve water tightness and durability for long-term performance over 120 years. But secondary lining is extremely challenging, trying to get a very high quality finish over such a long length. But we're surging on ahead there. Some very good work being done. Central, well on with that now. And west, we've started within the last month. And touch wood, everything is going okay to date. Marine logistics, to date we've moved nearly 4 million tons by river. That harps back to that key fundamental to try to remove everything from roads as much as possible. These are some of our tugs. I think that's our tug Felix on the top right, pushing. That's the West TBM about 5 years ago, pushing the components of the TBM up to Carmouth. And that's one of our eastern TBMs. I think that's Selina coming in probably around Christmas time. I think this was on TV. Some of you may have seen this, but again, a pretty cool sight to see. Not something you see too often in London. So an example of our sites in the sort of long term, what we're trying to achieve. Putney Bridge, very aesthetic location. This is the start of the boat race here. Very prominent location for us. That's some rowers on the river. What we're trying to achieve here is something like this. So we've got a foreshore structure. We're intercepting flows which are discharging just underneath the bridge here, conveying them over to this foreshore structure and down a shaft and into the tunnel. That's the aim of the game. That's what we're looking to achieve, and we're very close to that now. I think I've got an aerial shot coming up. This bottom photograph here is taken about maybe a month ago. That's an aerial view of a very tight, compact site, but very tidy site. Very proud of what the team are doing there on that and all of our sites, to be fair. Another example, this is Blackfriars. So this is before, this is circa 2014, the old boat pontoon there. I've shown you this previously. This is what we're trying to achieve. In order to facilitate that, we built a new jetty, a new Blackfriars pier downstream of Blackfriars Bridge for the boats to moor there, and then that allowed us to get on with this, which is the Blackfriars foreshore structure. Again, some really nifty construction that's gone on here. One of the challenges here was how to build a long connection culvert from out underneath the bridge here on the right hand side all the way to the shaft on the far left. And there's a series of slides here which basically show that just before Christmas the team floated nearly 35 meters of concrete culvert was constructed in a dry cofferdam and then floated into position. And I'll just quickly flash through a series of slides which show that being done, but a very, very impressive piece of civil engineering done by the team there at Blackfriars. And that is a picture of it being floated into place this last year. And ultimately, Blackfriars, this is what we will achieve in a number of years' time. I've said circa 2021 there, but I think given COVID, it's going to be a little bit later than that. But some environmental betterment I've mentioned. This is an intertidal terrace at Dormey Street, designed to provide habitat back to that river. Some of our kiosks have cladding on it, which can provide habitat for various different creatures. This is our site at Barn Elms, where we've got a 1.1 kilometre road that needs to access this site in the long term, and we're using a material called truck pave there, which is effectively trying to avoid as much as possible a sort of a hard surfaced area that needed to be drained. This is sort of harping back to sort of suds and allowing as much natural drainage, but still giving us a hard standing area that we could take 40-ton cranes down on every 10 years when we need to open the lids on the shafts and get into the tunnel. A quick flash over procurement and delivery, just to say that the overall client on the job is Bazalgette Tunnel Limited, which is a sort of a private entity, an infrastructure entity. I won't dwell too much on that. This is an overview of the delivery partners involved. So western section, my area, which is West BMB, which is Bam Nuttall, Morgan Sindel and Balfour Beatty. In central we've got Flow, and that's Ferrovial, Lang O'Rourke, and then out east we've got CVB, which is Costain, Vonshi and Solantash Bashi. And Amy are the system integrators, so they'll primarily be involved in this sort of SCADA and bringing together the telemetry and the operation of the scheme at the back end. And Jacobs, whom I'm engaged with, is the project-wide program manager for the whole of the works. Ready, look ahead. This is a project schedule. This doesn't really incorporate COVID, particularly at this moment in time, but it just gives a broad overview of when we're looking to hand over, which is broadly around 2025 into 2026. But the best part of the construction will be certainly complete by the back end of 2023. And there we go. I think we're close to the end. That's a visual shot of Putney Embankment in its final layout. You can just see we've got a bronze strip which runs across the scheme. That's the start line for the boat race. So that's really sort of celebrating what's going on there in the locality. And this will be a very prominent feature when you see the boat race on TV. And that's the new Bazalgette embankment at Blackfriars, as it will be called. And that's the conclusion. So just to say, this is a project not just about building a tunnel, it's about building a lasting legacy for London, its residents and its visitors. That's been really important to us, and hopefully we're going a long way to achieving that. And I think that's it. I've overrun by about 8 minutes, but I hope you can forgive me for that. Gosia, I'll hand back to you. Or any questions?
What an amazing project. Well, it has been fantastic to listen to your presentation. Thank you very much, Colin, for giving us an insight into this project. Before I go to the questions, I would like to say thank you to the Infraco Consulting for sponsoring this event. So thank you very much. Now we've got a couple of questions, if I start reading them. So the first question was, did the drop tubes come in segments?
Some of them. So some of them are short enough to fit on one Arctic. That Hammersmith length has come in 2 sections. So the main straight section has come on an Arctic, and then the Vortex generator that sits on the top, that's come in a second section basically. But
okay,
welded connections throughout.
Okay, yep. Thank you.
Okay.
How are the names of TBMs chosen?
Oh, that's a big complicated issue. I'm not even too sure how we did it. There was certainly a competition run internally, and we were looking to TBMs are always named after ladies. That they're always given female names. That's a tradition in tunneling. and we wanted to name them after prominent ladies in the local boroughs who sort of had a STEM influence, an engineering or sort of technical influence, or had some great influence on the locality, and that's where the names stemmed from. And then there was a sort of a competition to pick those names out of some sort of a hat somewhere, done by very important people, and then we ended up with those names.
Good, promoting women in engineering.
Absolutely. Yeah.
Next question: what was the supply chain for the works, design and construction?
Oh, now you're asking. I mean, I think we're probably drawing in everybody. I think I've mentioned the main JV partners there: the BAM Nuttall, Morgan Sindel, Balfour Beatty, Ferrovia Lang O'Rourke. Amy, our main penstocks and flap valves, they're being delivered by Ham Baker. I think a lot of our electrics have been delivered by Boltings. But I'd be surprised if I think most of the water industry is engaged on Tideway in some format at some point in its time. Too many to mention.
Possibly that would be easier to list whoever wasn't involved than the other way around.
Possibly, yeah.
Okay, another question. Question about maintenance. Can the system be shut, let's say, in 20-30 years for the maintenance?
Yeah, so the plan is that we will shut down the system every 10 years if we need to, and we have the ability to get down into the system. We close those penstocks, discharge would revert to the river as we have today, and then it'll be a case of getting in and inspecting the structures and hopefully not finding any problems and closing the lid again. In terms of our high level structures, the sort of hydraulic penstocks and flap valves, they'll obviously be inspected a lot more regularly than 10 years. We're expecting sort of 6 monthly maintenance visits and visits to the kiosk, not every couple of months. But yeah, and access and access and safe access over 120 years in these sites has been a massive challenge, and standardization of access across multiple contractors and multiple designers has been a real challenge to get that right. But yeah.
Another question: was there any desire to generate electricity from the high velocity flows?
Yeah, that's yeah. I mean, as an engineer, I've thought that would be a very wise thing to do. I think when you get into the delivering that and the maintenance of such an element, it just quickly became non-viable. You're dealing with a sewage system which has sufficient amount of material in it, so ragging and damage to any sort of turbines or blades would be a massive issue. And I think from a sort of a consumer value for money and getting back to the original scope of we're here to intercept sewage, the complications of trying to generate power from that sewage were extremely onerous and would have led to massive cost increases and certainly an intensification of the amount of infrastructure we'd have at each site. So it was thought about, and it was thought about quite hard. I was involved in that, but it wasn't viable.
How is the project funded?
It's privately financed. It is ultimately there is the government does have a backstop on the project, but it is delivered by Bazalgette Tunnel Limited, so it's pension providers, as I flashed up on that. I think it's Allianz and a number of others who ultimately fund the scheme in tandem with sort of Thames Water bill payers. There's an element of the Thames Water bill goes towards this scheme.
Okay, I'm conscious of time, so quickly through a couple of questions more. Are there any other cities around the world interested in copying Tideway?
Yeah, we have had interest. We've had visiting delegations from a number of cities across the world. I certainly know from the east. We've had some Chinese delegations. We've had a team from Singapore that I've hosted, as well as American teams. We ourselves built on experience in the States, particularly Portland in Oregon was a big one we used to help us. But yeah, I think certainly around the transients and the sort of hydraulics and the work we've done on long-term durability, making a scheme last 120 years, there's a lot of lessons learned.
I've got another question. How would you summarize the overall approach to health and safety and the health and safety record on the project?
I would say it's exemplary. I think, Tideway has set out from the start to set the bar extremely high. I would have liked to have given a presentation on health and safety alone, but we've striven very, very hard to sort of reduce the curve of accidents and fatalities that you see on major infrastructure projects, certainly in the UK. And to date, touch wood, touch everything, we've done extremely well. We're very proud of what Tideway has done. We've set out to try to lift the standards of the project, of the industry. You know, we have something called EPIC, which to me is fantastic. It's actors basically. You know, we place our operatives and all of our staff in EPIC who experience an accident on site, experience what it's like to be involved in an incident and an incident follow-up, and really try to get the point across that accidents don't just occur due to an error by an operator on a site. Sometimes those accidents are caused by decisions taken a year, 2 years, 10 years beforehand, and everyone is involved in safety. And we have something called the right way. We either do it the right way or we don't. And everybody has the right and the power to stop work if that is what's needed to be done. So I'm very, very proud of that. It's pretty good.
Well, that was the last question. Thank you very much, Colin. Absolutely amazing project. So thank you for giving us this presentation. Before I close, I would like to say thank you to Catherine for helping to organize the event, and to our sponsors, Infraco Consulting. And just a quick note before I wrap up, that the deadline to enter the Pipeline Industry Guild Technical Awards has been extended by a week, and it's till 23rd of April. Please check our website for the future events. And then also we're planning more events next month and the following months from the Southeast branch. So please keep checking.